Okay, let's start off with the definition of inner product. So if we take a look here, if U, which contains of U1, U2, U3, and so on and so forth until UN, and V, that consists of the elements V1, V2, V3, and so on until Vn, are vectors in spaces Rn, R to the power of n, then the dot product, or known as the Euclidean inner product of U and V, is denoted by U dot V, and is defined by U1 times V1 plus U2 plus V2 plus U2 times V2 plus U3 times V3 plus so on and so forth until UN times Vn. So to further explain, let's take a look at this. So here I have the example. I have A, which consists of A1, A2, and A3. I also have B, B1, B2, B3. So using the definition, let's write down the definition of inner product. So a thicker one. U dot V. U1 times V1 plus U2 times V2, so on and so forth until UN times Vn. Okay, so let's see. We have A and B. Let's conduct the inner product. I'm going to choose my color here. I'm going to use green and I'm going to use red so you guys can visualize it better. Okay, so let's start. So we are going to get the dot product of A and B, right? And so let's write it down like this. A dot B equals 2. So we write down so if we take a closer look here, this deriving from this definition sorry, we can derive that A1 is U1, and then A2 is U2, A3 is U3, and then so on and so forth, but I only have 3 elements here. And then who's V1, V2, V3? That would be from B. So it'd be V1, and then V2 is V2, V3 is V3, like that. So if you're deriving from the definition, right? So let's start. A1, we're going to multiply that with B1. And then we're going to add this with A2 times B2. Okay? And then we're going to continue for A3 times B3. Like that. Pretty simple, right? So let's try with numbers this time. Let's say that A1 is 2, A2 is 3, and A3 is 4. Let's say B1 is 1, B2 is 0, and B3 is, let's say, 2. Okay. So now that we have already derived from this definition to this, let's start writing it down with the numbers that we have. So A dot B. So who's our A1? Our A1 is 2. 2 times who? We have B1. Who's B1? It's 1. Okay, and then we're going to add it by A2. Who's A2? We have here number 3. 3 times B2. Who's B2? 0. So let's multiply 3 by 0 and then add it. So we have A3 times B3 here. Who's A3? We have 4. 4. And then we're going to multiply it by B3, which is 2. Okay, let's count it now. 2 times 1 is 2, plus 3 times 0 is 0, plus 4 times 2 is 8. So now we have the dot product of A and B is 10. And because the dot product consists of multiplications, they have its properties. So let's take a look here. The first property is called the symmetry property. So the symmetry property says that the dot product of U dot V is equals to V dot U, because this applies to any kinds of multiplication. So it's basically as simple as, like, if you multiply 1 by 2, it's the same like you multiply 2 by 1, you know. And deriving from, if we take a look at this, and if you want to further prove this this property, we can use this from our example before. So we have here A dot B is 10. Let's try with B dot A. So let's multiply 1 by 2 plus 0 by 3 plus 2 by 4. So this one is 1 by 2, sorry. 1 by 2 is A1 times B1, no, B1 times A1, sorry. And then 0 times 3 is B2 times A2, 2 times 4 is B3 by A3, like that. So we'll get 2 plus 0 plus 8, still 10. So this first property is proven. Now let's move on to the second property, which is the distributive property. Let's write that down. So what does distributive mean? Distributive means that it's distributing, right? So we have U dot V plus W, and it's equal to when you get the dot product of U and V, and then you add it with the dot product of u and w. So let's try to prove the second property. We have u consisting of 0, 1, and 2. We have v, we consist of 3, 4, and 5. And then w is 1, 2, and 3. Okay. So the distributive property is u dot v plus w is equals to u dot v plus u dot w. Let's prove that. Let's start with this one first. Okay, let's try to get this one first. What result can we get from that? Actually, you know what? Let's just do it at the same time. Why not? So let's add v plus w first. So v plus so v plus w would be 3 plus 1. 3 plus 1, that would be 4. And then we have 4 plus 2, that would be 6. And then we have 5 plus 3, that'd be 8. So v plus w is 4, 6, 8. And we're going to get the dot product of u and this. So let's start. We have 0 times 4, 0 times 4, plus 1 times 6, plus 2 times 8. Okay, and then let's take a look if we distribute, right? So we have u dot v. So that would be 0 times 3, plus 1 times 4, plus, let's put that in brackets, 2 times 5. And then we're going to add it by u dot w. So u dot w, 0 times 1. Sorry, I'm not really consistent with my dots, sorry. U times 1 plus 1 times 2 plus 2 times 3. Okay, let's try. I'm going to calculate this by myself and let's see where it takes us. And turns out that they're both the same. So this property is proven. And due to the limitations of the duration of the video, I don't think I can explain all the properties. But the remaining two properties are, we have here, this is called the property. So you can see here we have k as a scalar, and then you have multiply the scalar by the dot product of u and v. But actually, you can also multiply the scalar with u and then get the dot product of that with v. And the next one is called the positivity property. So it sounds like this. So v dot v is greater than 0 and v dot v if and only if v is equal to 0.
Okay, now let's work on this problem together. We're given three factors, u, v, and w, an inner product space along with some inner products and norms. Our goal is to evaluate each expression without knowing the actual factors, only using the property of inner product. So let's start with questions 27. We want to find the inner product of 2v minus w and 3u plus w. The key idea here is that the inner product is linear, which means we can expand it just like algebra. Okay, so first step, write this: 2v minus w, 3u plus w, and 2v plus 2v, 3u plus 2v. Now we pull the constant out of each inner product. So we have the 6 one, vu, then 4vw, 3wu, and minus 2wu. Next, we substitute the values we already know. So we know that u and v is 2, so we write this. For vw it's minus 6, and 3w and u is minus 3, and 2w it's 7 cubes. So now we just calculate 6 12 minus 24 plus 9 and 19.8. The result is 101. So the final answer for question 27a is a minus 101. Let's do the next question. Now let's move to the part B, which asks for the norm of u plus v. Whenever we see a norm, it's usually easier to square it first. So q plus v, q plus v. Now we expand the inner product. qu, uv, vu, and ev. Substitute the known values. What is u and u? It's 1 cubes. U and v is 2. V and u is 2. So 2 and v is 2 cubes. So 1 cube is 1, 2 plus 2 is 4, and 2 cubes 2 is 4. So 1 plus 4 is 9. Now we take the square root. Square root is like this. 3. This is the result. Next question, 28, part A. We use linearity and expand everything carefully. So the question is u, v, to w for u and v. So calculate for u plus u, v, v for u minus v plus v. No. And minus 2w for u minus 2w v. Pull the constanta to out. So this will be 4 u and u plus u and v minus 4 v and u minus v and v minus 8 w and u minus 2 w and v. So substitution the known values. What is u? And u is 4 1 2 4 2 4 minus 8 minus 3 minus 2 minus 6. We calculate 4 times 1 is 4. 2 minus 4 times 2 is 8 minus 4. 8 minus 8 times minus 3 is minus 24. And minus 2 times minus 6 is positive 16. Positive 12. So we got that. 30. So the answer for 28A is 30. Finally, the last question is 28 part B. Again, we square the norm first. So 2w v cubes 2w minus v w 2w minus v. Expand 2w and minus 2w and v minus v 2w plus v and v. Pull the constanta and substitution. So 4 w 2 minus 2 w and v minus 2 again v and w plus v and v. So what is w and w values is 49. And what is the value of w and v is minus 6. What is the value of v and w is also minus 6. And what is the value of v and v is 4. Calculate 4 times 49 is 196, and plus 12 plus 12 2 4 plus 4. So the result is 224. But we have to square root. What is square root of 2024? 224. 224. It's like a 16 times 14. So the result will be 44 for square root 14. So the key takeaway here is that inner product problems are all about expanding carefully and using the given values correctly. As long as we stay organized, we don't even need the actual factor. That's it for these problems. Thank you for watching.